Hello everyone, welcome back. So in this video we are going to understand the contest third question, number of integers with pop count depth equal to k, and question number second we have given. Okay, means number of integers with the pop count we have to find and where depth is equal to k. Okay, so first of all understand what is the pop count. So pop count is, let's suppose I'll say pop count, let's suppose like this, and if I will pass x, right, means the argument is x, means the number of 1s in the binary representation of x. X is a number, right? And what is the number of 1s in binary representation of bs of x, we can say that, right? Let's suppose, for example, I'll take a pop count of 7, right? Let's suppose I'll write here itself 7. What will come? Give me a second. What will become here? Pop count of 7. What will come here? It will come 111, right? Binary of 7. What is the binary of 7? Binary of 7 is nothing but what? It will come 111, right? You remember the formula 8421, right? So 1 1 is 3 and this is 4 is 7, so we can get 7 right here. So 111. Now we have 3 sets bits, right? So what we call is a 3 set of bits, we can say, can we say that? And that is why the pop count of 7 is 3. Understand? Means, and now understand what is the pop count. You understand the pop count, right? What is the depth of pop count depth? So it is how many step it takes to using pop count to reach 1. So let's say I'll go with this px is equal to 0, right? So let's suppose p0 is nothing but x. Okay, so can I say p1 is what? Pop count of p0, and p2 is a pop count of p1, right? This is p0 and this is p1. Can we say that? Means you already have, if p0 is equal to x, means we'll say p1 equal to pop count of p0 and p2 is pop count of p1. Can I say that? So similarly we can say, let's suppose there's pd something, okay, and pd is depth, right? Pop count of depth is equal to, it comes once. When it is comes, this is called this is, we can say, this depth is called, what is called, the pop count depth. This pop count depth, you remember here, it is pop count depth. This is pop count depth, right? When pop count depth is equal to 1, right, there we can say this is the pop count depth, right? So let's understand again. So let's suppose you have given let's say you have given x equal to 7. Can we say that? And you know the binary of 7 is nothing but 111, right? If you say pop count of 7, can we say that? Pop count, write the pop count. Okay, pop count of 7 is nothing but what? 3, and depth we have to go what? Is 1, correct? So when we say pop count depth is 3 this time, because we have calculated this, right? So this will become, let's suppose, 2. So depth is nothing but what? Is 2 here. When we'll do the similarly pop count of 2 this time, what will come? 1. So here depth will become what? Is 3, correct? Now we can say that pop count depth is 7 is nothing but 3. Can we say that? And that is why if you see the example, you will see that we have given this one. Let me go there. Okay, so this pop count, saying pop count of x is defined as the smallest integer d greater than or equal to 0, such that pd is equal to 1. Means the depth, the d is the called depth count, right? So when pd is equal to 1, that is called the smallest integer, right? And that is why, for example, it is saying if x equal to 7, we'll do the binary representation 1, and the depth is coming what? 3 2 1. So the depth of 7 is 3. Can we say that here? the depth of 7 is 3. So let's suppose we have given the example. So let's suppose we have given this num we have given and these queries we have given, right? So if we'll say 1011, so the count numbers in what nums at 0 to 1. Can we say that? Means whose pop count is depth is 1, right? Then we'll say 211. We have to, let's suppose we'll say update nums at 1, right? And it is 1, right? Then we'll say count number of nums in what we call 0 to 1, whose pop count is depth is 0, right? Means when we say the count the numbers in this range, right? What we will get, the depth count will get 1. Here we'll get we will update the nums at 1 is 1, right? And we'll update it. So we'll get what? 211. Again we'll count the numbers in the 0 to n, right? In the in this value, what we'll get, the depth count will get 1. Let's suppose what I'm trying to say, initially nums at 0 is, let's suppose 2 we have given. Okay, so what is the binary representation of this one? Is 10. Can we say that? So the pop count, if we'll take the pop count is 1 and its depth is coming what? Depth is coming is 1. Can we say that? Similarly we'll do pop count of at nums at 1, right? Nums at 1 here, what will get here? 4. What we have? 4 we have. So in this case what we will get here? Binary representation 100, and the pop count will become what? Pop count is nothing but what? 1 is become the depth is 1, right? Means these are the queries we have given. Let's suppose queries 1, queries 2, queries 3 we have given these queries, right? You have given the nums 2 and 4 we have given. So nums at 0 we are getting 2 and its depth is coming 1. Nums at 4 depth is coming what? 1 again, right? So you will pass these values, correct? Now we will do the binary representation. You will get like this, right? Depth count is coming like this. So what you are doing, you will give me a second. So here you have this query, right? So very first query, query 1 we can say, what is the range we have here? Left is at 0, right is at 1, right? Means the depth we can say is, with the depth is 1. We know for the depth this one is nothing but 1. Depth is 1, right? So both values are counted, valued 0 and 1, and so the answer is coming 2. Now for the nums when equal to 4, we know the depth is also 1, right? So we'll update the value, right? So what we call, we have to update nums at 1, right? So nums at 1 this time, previously 1, right? And its binary representation is 1 and its depth is 0. Can we say that? So we will update this, right? Previously we have already checked this, right? Our result is equal to 2. When we process query 3, we'll say we'll check the count between range 0 and 1, right? That we can see here, right? So what is the depth is here? We know that depth is 0, right? So we'll say depth is 0. Okay, only if nums at 1 qualifies the result is equal to 1, and so the result is coming 1. There is only 1 coming, so this is result is 1. Here is coming 2 valid paths, so we can getting 2, right? So answer is coming this 2 and 1. Here it is not coming because we have updated the nums, right? And its binary representation is 1 and depth is coming what? 0. Remember? And that is why it is coming like this. Okay, so you can say that there is 2 valid answer, and those valid answer you are adding into the result output. So let's understand the code. Okay, so to understand the code, we should understand the intuition, right? So what is our intuition? So we are asked repeatedly that count how many numbers in the subarray have a specific pop count depth, right? And we have to update the value in the array dynamically. So that sounds like a range query with the update problem. You remember? If you have already done the problem, it's based on the Fenwick tree, right? You can say binary index tree, and you can say segment tree. So you can use segment tree or binary index tree, right? And you can do that, right? So but there is a twist, right? There is only 6 possible pop count we have from 0 to 5, right? Since the pop count reduces value fast, right? So what is the approach that will be efficient for us, right? So very first, if we have observed that, right, what we have used here, you remember the pop count pre-compute we have done, right? So what we will do, we'll pre-compute the pop count, right, for each number, and then we'll maintain the Fenwick trees. If you remember what is the Fenwick tree, I'll tell you in the other video. Just think that we will maintain the 6 Fenwick tree, right? And then for each depth, let's suppose from 0 to 5, we'll pre-compute the value, right? So understand what is Fenwick tree. I'll go through in the depth later, but just think that give me a second. What is Fenwick tree, right? What is Fenwick tree? So Fenwick tree is a data structure that efficiently supports, let's suppose for the, if you remember, the prefix sum query, right? If let's suppose from 0 to I we have go, from 0 to I we have to go, right? Means the prefix sum query we are going, right? So it is taking what? O log n time, right? So it is efficient, right, for the time complexity based. So Fenwick tree, what is doing, it supports the prefix sum query, right? And the point update query, you can say, right? Point update query, let's suppose if you are doing add or subtract at index, let's call I. If you are doing these things, so this Fenwick tree, it is supporting this, right? So when we are using the prefix sum, it will take time complexity O of log n time, right? And similarly, if you do the point update queries, right, like that, means either you are doing add, subtract at any index, right, it also taking O of log n time, right? So it is used of a full segment tree when we only need a range. You know, you have seen the range sum query, if you remember, right? If you don't know, let me know in the comment section. I'll create another video for you. Okay, so it is used only instead of the full segment tree when you only need what? The range sum query. You want faster and simpler implementation, so the values are updated frequently, right? And that is why we will use this concept here. So what I'm trying to say here, so our approach, right, our approach will pre-compute the, you know, the pop count we have seen, right? Pop count depth, right? That we will compute for each number, right? Very first step, what we will do, we will pre-compute the pop count depth of any x, right? The x is for each number, we can say, right? Then we will maintain a 6 what you call Fenwick tree. Can we say that? For one of each depth. How? From, let's suppose the depth is between, let's suppose it's saying 0 to 5 in the range, right? And for each nums at I, you know, the nums at I we have given, right? Nums at I is an element in the nums array. So for each nums at I, we will find its depth and will update its corresponding bit, right, at position call I. Understand? This very first, what we will do, we'll pre-compute the pop count depth x for each number, then we'll maintain the Fenwick trees for each depth that is between the range 0 to 5 we can say. And for each nums, right, for each element at I, we can say in the array num, we will find the depth and will update its corresponding bit at the position I. Then what we should do, we'll answer the query, right? What we need to do to answer the query, there are two things we have to do. If type is between the range, let's suppose 1 to L R range will take, and then K. So if the type is like this, 1 left, right and K, means we will use bit at K, right, to the sum in the range left to right. Can we say that? Means we will use here, let it call bit. How we are saying that? We'll take a bit at K, right, and this bit at K should be in the range left and called right. In this range it should be there, right? And the query we have another, let's suppose call query 2. After this we can say is what if it is type having here not 1 but it's a 2 IDX index we can say, and value. That we have seen 2 type was there, right, in the example. In this case we will remove the nums at given index, right, from its odd depth tree, okay, and we'll add the value to the new one. Remember the example that we have seen, index at the query 2 that we have seen, right? If the query let me show you. So as you can see, right, when we have seen these queries, right, so when we are seeing this query, what we have 2 1 1 means the 2 is the value we have, then we have index we have, and then we have value, right? Means this case we will remove the nums at index, right? What is the nums at index? Index is 1 here, right? So what is the value is there at 1? What we have value 1, means we have removed that, remember? So once you will remove this nums from so its old depth, from its old depth tree, right? So what will happen, we have to also add the value, right, to the new one, right? So we'll add the new value to the new one, right? So what will happen, we will add the value in the next one, right? So what we will do, we'll remove the value from the nums, right, and we'll say its old depth is gone, finished, so there is no depth is there, okay, but the value we will add into the new one, and that is why we have to add the value here, okay. Like that we will continue and we'll do the process, okay. So can we say that very first we will pre-compute this pop count of x for each number, then we'll find the we'll maintain the 6 Fenwick trees from 0 to 5 depth we can say for each one for each depth, and for each element at I we have to find the depth and we have to update bits at I, corresponding bits at I position, right? Then we'll check the type. If type is start from 1 L and R in the range and then K, there is 2 type is the range query, we have seen that, right? So in that we will update. Otherwise if the type is different, if the type is coming to I index and then value, right, that we have seen, right? So we will remove the index at nums at index this value, and we will update the old depth tree and we'll keep adding the value in the new one that we have seen, okay. So it overall we know that the Fenwick tree will take what is the calculus, it will take the complexity O log n, and that is why for each operation either using updating and then using the query, it will take the O of n log times. It is efficient and that is why it works for us, okay. So let me go here. So very first what we need to do, we will define a class, right, that is called bit, right? So this bit class will define a binary index tree that is called Fenwick tree, right? What we call, now let me write here, this is a binary indexed tree, nothing but it is called what, Fenwick, right? week, you will check the spelling. Okay, this is the fine week tree that we have to define in the very first step. So this will have the update queries, right? And we have the queries we have, and update we have operations, and the range query we also have here. Okay, means if you talk about for each bit, how we are going to track how many numbers have the depth equal to k, right? So we will build actually let's suppose bit at 0. This is the bit class. So bit at 0 will say nothing but depth, for depth 0. Similarly, we'll take 1, bit at 1 for the depth at 1. Similarly, we'll keep going until, let's suppose for the bit 5 we told, right, till that for the depth 5. So for each bit it work like there is nums index is there. Let's suppose nums index is 0, 1, 2, 3, 4 and 5. These are the index we have. So this each index will treat will take as, let's suppose, bit at k we can say, and then we'll update what, I, and then +1. It means nums at I has a depth k, like that we will see. Okay, so that we are taking these values here, right? These are the range we have here. Next we'll compute the we'll pre-compute the pop count depth. Let's understand. So next step, what we need to do, we need to define the pop count, means we have to pre-compute the pop count depth, right? And for that we have to create this thing, right? This functionality you can say, means each count, we are counting the number of 1s in the binary, and then we are updating, right? So let's suppose very first it is coming 7, right? Means it is 111, right? So what is the pop count? You have seen, right? Pop count, it is coming 3. Then let's suppose it's coming 3 this time, right? So pop count is 011. This time the pop count will become 2. Then what will come? Pop count is 2, right? Then it will become what? 010. So this time pop count is what? 1. Means total depth is what? Total depth is 3. So these things we will do at here. Okay, then we will initialize the what you call bits of the current nums, right? So you know that we have to pop count depth, right? So what do you need to do? We'll go to the range from 0 to what, 0 to what do you call 5, right? And we'll update the value. That we will do. After that we have to initialize the bits of the current nums. For that we'll go from 0 to n, right? Here we'll get the depth, current depth, and we'll update the current depth. How? Let's say we have nums we have, right? And this nums is, we have 2 and 4. Can we say that? So 2 means 10, right, in the binary, and the depth is what? Is 1. Another we have is 4. So depth is 1, binary is 100, and depth in this case is also 1, right? So if we'll convert into give me 1 second, if we'll convert this into bits at some value, let's suppose I'll call it I'll write it here. Okay, so I'll say bit at 1, it will become what? It will become 1 0 1 1, right? 1 1 0 and 0. Can we say that? And so on here, right? And other bits are what? Is 0 0 0 and so on. Understand? Further, once we have these things we have handled, right? Now we have to handle the queries. So let's understand how we are doing what do you call, how we are handling the query. So if you see, we have queries we have given, right? So over the queries we will iterate. So these are the query L, R, K, we know that, and two type of the things we have, right? All the queries. So let's suppose the nums was, we have what? 2 and 4 was there, right, in the array, and the queries we have is, what are the queries? First query is what? 1 0 1 and 1 was there, right? another queries we have is, let's suppose this is query 0, query 1, and another queries we got 2 1 1, and another query is query 2 is I think it was 1 0 1 0, I think, yeah, 1 0 1 1. Means if you do the count, pop count at here, it is equal to 1, and this is true. Then we are taking nums at 1, we are updating as 1, right? At here you can see. Then once you will update nums at 1, because this is the index, right? Index nums at 1 we are updating 1, remember? And here pop count is doing what? Pop count we are getting depth is equal to 1. Here pop count depth is coming 0, remember? So very first, when you get the query at 0, let's suppose we are talking about this one. If query at 0 is coming 1, right? So what are the ones is coming? 1 is here coming and here is coming. Means we are talking about these two, right? Means very first what we need to do, we have to check the depth query. Can we say that? So depth query, nums at 0 is what we have, is 2 we have, right? And so the depth is coming at what? 1. Similarly, nums at 1, what we have? 4. Depth is also 1. Can we say that? Means result is 2. So like that, we'll keep checking these values and we'll keep adding here, right? And for that, you have to check all the things here. Let's suppose for the query 1 we are going, we'll get L, R, K, right? We will keep checking this value and we'll keep adding unto the answer. So once you updated the answer, you will keep adding the value here, okay, on the answer, you can say. So bits at K, we have this range L and R, and you know the other cases, right? For the other cases we have to update it, right? So we are updating here, okay? So that's all we have in this video. If you have any doubt in this video, please let me know in the comment section, okay? And thank you guys, thank you for watching this video, and let me know in the comment section if you need anything. I'll provide you in the comment section. Thank you for watching this video. I'll see you in the next one.